Yeah, if I'm feeling absolutely horrible from my vaccine dose on Tuesday, then I won't be coming to class.
Okay, you're getting your second one?
Second one on Monday.
Okay. Yeah, if you had a bad reaction to the first one, the second one isn't that bad. Yeah. Is what they found. If you had a
almost no reaction whatsoever to the first one.
Okay, so then you might be sick. You might have the flu. Kind of feels kind of flu-y. The first one did for me. But I never stopped doing anything when the world stopped doing things, but I just did what I did, which meant I wasn't exposed to very many people because no one was out and about except for me. Got myself declared an essential employee last summer so I could go to work. And I was an essential supervisor of an essential employee and one essential employee. And then I convinced them that we had to have a second essential employee in there because we had to do training on one of the employees. And the next thing we know, people just started trickling in the lab as they felt like it. Everybody's essential. No, not everybody's essential.
All electrical engineers are essential.
Not all electrical engineers are essential. I worked for a few people, I would argue that way. Okay, so anyways, pre-lecture 18 was due today. Wait, that's not today. Oh, it is. Okay, so we had a pre-lecture due and a project due. Okay, I'm right. I was wrong. Zach's right. On Tuesday, nothing's due. We'll finish up Flash. There'll be a pre-lecture. It's in the Emergent Memories folder. I just went ahead and opened all the folders. They've been there, but they've been invisible. So only 2 more pre-lectures left. And then the final is optional if you fill out the course evaluation. So this is chapter 2 of the Micheloni book. Hopefully no more pictures of film canisters or anything like that in here. Different types of memory, random access. This is like NOR flash. But NOR flash is non-volatile. But usually inside of a computer system, we're using our random, let me just ignore this for now because this has nothing to do with this slide. Random access memory inside of a computer, what they refer to as the RAM of the computer, is usually DRAM. I had a whole nother point to the slide after I started writing on it. So the DRAM is volatile. You can read and write fast. And this is what you store the information, the code you're working on at the time, the movie as you're streaming it, you want it stored in something that you can access really fast. Now the read-only memory, this is for things that like set up your system and set up the system operation. You want this to be non-volatile, you want it to never go away, and you don't want the user to be able to change it. Then we have a third type of memory in here. The third type of memory that is generally flash in the form of an SSD, solid state drive. It's non-volatile, so when I turn the power off, it stays there. You want to be able to read and write to it. The problem is the reads and writes are relatively slow. So this is why we have to have these 2 types of memory inside of our computer. If we could find a type of memory that was both fast and non-volatile, that we could get terabytes of data in, we could have the density in, we could just combine these 2 and simplify a lot of the bus operations inside a computer and probably speed things up considerably.
Well,
we don't need the DRAM.
Yeah, we don't need the DRAM.
Yeah.
It really speed things up.
It would. And simplify computer design.
Are we anywhere close to them?
Well, this is what we're going to talk about next. After Flash is ReRAM and DRAM, and I think those are potential candidates for that. It's a matter of getting the density up. And I think the one that's going to get there first is ReRAM. Now this is our floating gate memory cell. This is the funny little transistor symbol. And that just means that extra line in there means I have an extra gate. Looks like a regular transistor. What I'm going to do is put high voltages on the control gate relative to the substrate. So I put a really big voltage across here. I can force electrons to tunnel through into this gate. When there's electrons trapped in the gate, the threshold voltage increases. I can also, there's another way of doing it. What I just described was Fowler-Nordheim. The channel hot electron injection we do by forcing a high current between the drain and the source. And some of the electrons have enough energy they can tunnel through and go up that way. So two different ways we can inject charge into that floating gate. Okay, this is a NAND string, and this is what we're going to be talking about today, is what's different about NAND. NOR flash pretty much works like DRAM. So the one that's a little bit different is this NAND flash. And the reason why we call it NAND flash, first of all, we have 32 or 64 cells in the string. So this is drawn like there is a word line 0 to word line 63. Like I have 64 cells in the string. There's two select transistors, the DSL and the SSL, at the end of the string, because these word lines are going to go all the way across the array and hit a whole bunch of different bit lines at the same time. So the bit line, the column that we're selecting, will be chosen by DSL and SSL. Bit line shared with two strings, yes. Oh, okay, so generally the bit line, we can share the bit line contact too with two different strings and double the effective size of the string. The word lines drive the control gate, and we'll look at the voltages it takes to actually read that and why it's called NAND flash in the next slide. I'm not going to get ahead of myself. No, we're not. We'll get to it in a slide or two. Now, when we talk about the basic unit of memory, I can get a page of cells out really quickly, because what I'm going to do is let's say I want to read word line 2. When I turn word line 2 on to be read, I'm going to have a whole bunch of different strings, NAND strings, that are tied to word line 2. And they're going to be presenting their data to their own little individual bit lines up here. And all those bit lines can be read at the same time. So what a page is all the bit lines that are addressed with that one row address. And we're going to read them out in parallel. And so we can get data out faster that way. So we're really not getting one bit of data at a time out of this device. We're getting an entire page. We're getting every transistor on that word line is going to be read out at the same time.
Don't we have to turn on the other word lines or something to get?
Well, yeah, we'll get there. We haven't gotten there yet. It's the grand mystery, and I realized this when Jack was in this class. It's like, oh, I know why it's called NAND flash now, and I was so excited. And I'm just waiting to get to this. Right now, we're just going to talk about how the outputs are going.
Why is it called? Is that something we're leading to?
Yeah, we're leading up to that. Okay,
Cool.
kind of, but we're going to talk about this is why when we address NAND flash, to get one bit of data out takes the same amount of time as to get an entire page of data out. So the effective rate I get the data out is much higher if I'm getting the entire page in a NAND flash. Okay. So this is a page down here. Now this is saying it's the smallest addressable unit, because when I address one cell, I'm addressing the entire page, everything that's connected to the word line. And one page is 4 kilobytes. So 4 times 8, 4,000 times 8 are the number of things that are addressed by that single word line. 32,000 bits. Okay, now the next thing I have, this is a page, that's the smallest addressable unit. A block is the smallest erasable unit, which is 64 pages. And the reason why it's 64 pages is because if you go back to that bit string, it's 64 rows long. I have to erase the entire NAND string at a time. And when I'm erasing the entire NAND string, I'm erasing everything that's on that word line as I go through.
I'm trying to think of a word that would be a combination of erase and address at the same time.
Erase and address.
It's not an actual word. I'm just thinking of.
When
Okay.
you erase something, you have to address it anyways.
Right.
Well, no, but like I'm just trying to mash the two words together.
Okay.
Okay, I'm going with that, I guess.
Okay. How about just erase, because you have to erase that you are addressing by default. Now there's another unit in here, and I don't understand where this comes from, but it's called a NAND, and it's 8192 blocks.
Huh.
And maybe that is just one NAND array, it's one total array.
There's 2 to 13.
Yeah, it's the size of the memory array. Let's just call it that for now. Okay, so I added this today because it didn't make any sense to me. I added this part, the VDD. We want to figure out what VOUT is. Now what I'm going to do is I've got some of the cells are programmed or actually are in the erase state. They have a 1 in there. And some of the cells have a 0 in there. There's a standard deviation of the voltage thresholds. And what I'm going to do is I'm going to turn on the read voltage to that transistor is going to be in between the threshold distributions for both the 1 and the 0. So when I tie this to VRead, if I'm in state 1, I have a low threshold voltage. So we're in state 1. My threshold voltage is low, so this transistor turns on, and VOUT will equal whatever's on the source line, because that will be a shorted out transistor. It'll be like a pass transistor. Now I have another potential state here, and that would be, let's say I'm in the 0 state. So if I'm in a 0 state, I have a high threshold voltage. VRead is not enough to turn the transistor on. So the transistor is off, and I've got VDD attached to a load with no current, because there's no path for current through the off transistor. So my output is going to equal whatever VDD is. So when I have a 0 programmed in, I'm going to read out VDD. When I have a 1 programmed in, I'm going to read out whatever's on the source line, which is probably groundish or a lower voltage. Okay, so that's how you read out a single flash cell if it's like in a NOR string. Now let's look, I hope this is it. Yes, now let's look at a NAND string, and you'll understand why it's called NAND. Jack was laughing so hard when I figured it's like, you could see the daylight going off. So in my head, the light bulbs, yes. Okay, so what I'm going to do first of all is I'm going to turn on the 2 select transistors, DSL and SSL. They're normal transistors, so I can turn them on with a normal voltage, VDD. I put every other string in the row, every other gate in the row that I'm not, every other gate in the string, sorry, there's too many things going on here. Every other gate in the string, I'm going to put at VPass. And V pass is a high enough voltage that it turns on both the 1 and the 0 transistors. So all these transistors are on. And this is part of the reason why it takes microseconds for this to happen. Because I have to turn on a whole bunch of gates on a whole bunch of transistors in order to read this thing out. I basically have to turn on every single transistor, not only in the string, but in the page, in the block. And that's why it takes microseconds. Now, this special transistor I have right here, the one that I actually want to read the entire page of data from, is going to be at VRead. So it will turn on or off. And so this is like a NAND gate.
Yeah.
With every single input tied high, except for the one I want to read.
Yeah.
Which may or may not be, which could be a 0 or a 1. You should hear some of the things I've made up about this to make it work with me where I understood what was going on. Okay.
Yeah, it literally just works exactly like a NAND.
And that's why they call it NAND flash. I like random access stuff, it makes sense. Okay, so this is the one we're reading. And when we read it, remember there's a whole bunch of bit lines, a whole bunch of NAND strings that are in parallel with this that we read out simultaneously to get our entire page of data at once. Okay. I can tell Jack I did that right.
The NAND slide, right?
How is it?
Next time I see Jack, I'll just like blurt that out.
Well, you won't see him for a while because he's still in Alaska. Yes, he's been in Alaska all year long.
Talk about quarantine.
Well, he got COVID while he was up there.
From like the 15 people that live in
No, from his parents.
Two of the 15 people that live in Alaska.
2 of the 15 people that live in Alaska. Yeah. So, and now they're vaccinating everybody up there, so he's getting vaccinated too.
My friend Glenn lives up there.
Who?
My friend Glenn lives up
Okay. I understand what it's like in the north. It's not terrible.
He likes salmon. He likes salmon fishing.
Yeah. There's good fishing in Saskatchewan too. North of where we lived in Saskatchewan, there was nothing but lakes and First Nations.
First Nations?
Lakes, woods, and First Nations, yeah.
Oh, right, yeah.
Okay.
It took me a second to remember what First Nations.
That is the Canadian term. Okay. Because they were the first people to have nations in Canada. Domino CMOS. Okay, we're gonna look at the schematic. Domino, remember, is another word for dynamic logic. So it has pre-charge and evaluate phases, just like it did in whatchamacallit in 380. And we're gonna use this idea with NAND flash to improve it in some weird way.
As opposed to pizza CMOS?
What?
As opposed to pizza CMOS?
Domino pizza CMOS something. Yeah, little seizures, whatever.
Little CMOS.
Little CMOS. Okay, sorry. So what we want to do here to speed things up a little bit is we can pre-charge that bit line up to a value, maybe like VDD over 2 or something like that. And we're going to use a higher level voltage for the pre-charge. So in this case, V1 is set to 2 volts, and the V threshold of my NMOS is 0.3 volts. So my V bit line when I'm pre-charging will be 2.12 minus 0.3 is 1.7 volts. That's my pre-charge voltage. And then for V2, let's do this part next because I won't have to write a differential equation for it. We're going to use V2 for reading. So V2 is a lower voltage, and in this case, V2 is 1.5 volts, and 1.5 volts minus 0.3 is 1.2 volts. Okay, now in between there, we've got to wait between pre-charge And when I'm reading it, I'm going to have to wait long enough to charge up C bit line. And this is when I write the differential equation. The one that I used as an actual working engineer, I equals C dV dt. So we know that, what else do we know? We know the current through the cell. We know the capacitance. What we're trying to solve for is dt. So I do a little bit of fancy calculus here. D2 equals C over I times dV. So the amount of time I need to wait is, this is, I told you, this is all the calculus I did when I was working. 20 femto over I, which is 150 nano. And my dV is the change in voltage. Which is V2. My V2 is 1.5 minus the minimum V out that we want. So we want it to go up to at least 0.9. And we can calculate this. How long do I have to wait for this all to happen? Drum roll, please. 80 nanoseconds. So I can pre-charge it in 80 nanoseconds, which looks a lot faster than the microseconds it takes to read out. So taking the time to pre-charge it isn't going to affect my readout speed, except it'll probably speed it up because now I'm starting from like this midline voltage range where I don't have to charge up that whole string because there's a significant amount of capacitance on this string. So I got a large amount of capacitance. If I'm trying to take one little tiny transistor that's addressed and use it to charge and discharge this entire capacitance, it's going to take a long time. But if I can pre-charge that string rapidly beforehand, I might be able to speed up the read. So that's the goal of this. This is how engineering works, is you start out with an idea that works and then you just keep on improving it over and over and over again until somebody comes up with something completely different. Okay, so this is the reading operation. We pre-charge the digit line out, the bit line out right here before we actually go through and do it. Why does that one have a line through it, Dr. Brower? I don't know. No, if you look at this right here, I'm talking about right here. Look, see that slide number?
Oh.
It's got a line through it. Like she didn't like it or something.
Crossed it.
Yeah, and I don't know how to do that, so it wasn't me.
Is Dr. Brower sending us a message from?
She has a lot of weird, oh, there are a lot of weird things she does.
Post-teaching message?
No, in all her homework files, there's hidden text. There's hidden text in all her homework files.
Like as in like written in like white space kind of thing?
Well, you can't see it. It's not even white space. It's hidden text. And if you go into the Microsoft Word settings and you click on the button that says show hidden text, a lot of times the solution to the homework is there.
What?
Which is why she never gave you Microsoft Word files. If you know that you have the Word file for the document, you've got the solution. Okay.
Huh. That's interesting.
Everything was in PDFs.
It's like a.
And I know they're still there, so that's why I give you everything in PDFs.
It's hidden.
It's just in hidden text.
Honestly, that's fantastic.
It is. It's amazing the Microsoft Word tricks she knew. Okay, so I want to program this thing. So I select the two select transistors. This one I'm going to put to ground. I put every row except for the row I want to program at VPass. So I turn on all of those transistors there and I put this really high programming voltage V pass is 8 to 10 volts. The programming voltage is 20 to 25 volts. I'm putting across a poor little transistor. And remember, some of these transistors are getting small enough, they have a 50 volt ESD damage threshold.
Seems rather dangerous to be doing.
Yeah, so these have got to be bigger transistors. Okay, so this is the row we're going to program. So we program, and we want to program maybe like this is the cell that we actually want to program. Wait, what's going on here? Ground. Okay, because see, this is at VDD, and this is at ground. This has no voltage. This is the one that's different. One of these things is not like the other.
Not like the other.
Too much Sesame Street. So this one's going from ground to ground. The others are going VDD to ground. So we've turned. This is the string we're trying to program. This is the row we're trying to program. What's going to happen here is I'm putting high voltages on the gate of this transistor. Oh, and I'm frozen. I'm putting high, I know you can see me in Zoom land. I'm putting high voltages on all the transistors in that row. So there's a potential that some electrons are going to tunnel through because they've got high voltages on it and get into the gate. And this is called program disturb. And I'll come back in a minute so I can actually see what's going on my computer.
What does that mean?